Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics. This lecture is entitled Bidirectional Shift Registers. Okay, so to this point, we've thus far discussed only shift-right shift registers. We've come in a number of different flavors: serial in versus parallel in, serial out versus parallel out, but thus far we've only been shifting right. So let's go ahead and come up with a basic functional diagram for something that can shift right and shift left. What I've drawn is this top diagram here, where when it's in red mode, i.e. shift right, what's going to happen is basically this input is being fed to that D, that stage's Q is being fed to the next stages, that stage's Q is fed to the next stage, that stage's Q is fed to the next stage, and finally we get a shift right output. Where are we going? We're shifting right. Doesn't matter what Q0, Q3 is assigned, it's your choice, okay? But we are still shifting right. In shift left mode, however, we have another input, okay? The input is right here, okay? That stage is the input now. That output goes to the, here, let's do this in a different color. So in left mode, we've got this stage is the input, and that stage's output goes to this stage's input, and that stage's output goes to this stage's input, and that stage's output goes to this stage's input, and finally out this direction. Despite all the spirals, which direction have we gone? We have gone left. And again, it does not matter which one you've assigned as the MSB or the LSB, you're shifting left. So that is the most basic functional diagram that we can come up with. Okay, there are two ins, a shift right in and a shift left in. There are two outs, a shift right output and a shift left out. So what is the shift right input? It's D red. What is the shift right output? It's Q pink. What is the shift left input? It's D pink. What is SL shift left output? It's Q red. Be aware that there are some devices out there where there is a single input. Okay, I know I just told you that there's two inputs, shift right input and a shift left input. Sometimes that single input is tied together. Doesn't necessarily make sense with this diagram. We'll show you in a later diagram how I can tie together those two inputs and use them as the same input. So what we're going to do in this next section here is basically put some logic in and show you how we can create these separate red, your right and left paths blue. So what we've got here is a really messy diagram, this logic circuit here. I've gotten rid of the clock and the clear signals there, but be aware every single one of these things are clocked on the same positive edge clock, and they could all be cleared out simultaneously. And it looks like a mess because it is a mess. There's a lot of things going on here. And it's almost like that parallel in shift register in our previous lectures. Almost. Let's go ahead and take each one of these things in turn. The mode. There is a mode. It's either in right mode or left mode. You can never simultaneously be in right or left, right and left. Okay. The way I've defined it, right is a 1, left is a 0. So let's go ahead and just look at one of the modes. Okay, in right mode, what's happening here? It's basically that mode command is high. It's a 1. It's enabling all these AND gates. What are those AND gates when they enable? Well, that shift right is being input. That stage's Q goes to that stage's D. This stage's Q goes to this stage's D. This stage's Q goes to that stage's D. Where's our output? Right there, as we'd expect. It's shifting right. What happens when we take that mode select to low, i.e. left mode? Basically, it's enabling all these AND gates, enabling this AND gate, this AND gate, this AND gate, and finally this one. If those are enabled, this is my input. It goes to D. This one's is the input for that D. This one's input is the input to that D. This one's output is the input to that D. And this is my final shift left out. Despite all the spirals, what have we done? Gone left. Let's take those two diagrams in right mode and left mode and put them together and add one final thing to it. Okay, what I've added here is this. This is my D input line. This is my single input line. It is being sent to both shift right in and shift left in. When it's in right mode, what's happening? Again, all the red AND gates are active. So this is right mode, right mode, right mode. That's my right output. When it's in left mode, what's happening here? It's taking that D input, that same D input. See this connection right there? And it's being fed back, back, back. This is my shift left out. If you want to go ahead and think of it in this incredibly complex fashion, be my guest. My advice to you is just think of it in our original configuration. When it's in right mode, it's going right. When it's in left mode, it's going left. Be aware that sometimes you can tie shift right in and shift left in to a single D input, regardless which mode it's in it's still going to use that single D input. Okay, so let's go ahead and try some more analyses of these bidirectional shift registers, perhaps using them in timing diagrams to see how they operate in different modes. Okay, so here is a bidirectional shift register. I've got a single input D. For this example, that D is always going to be held low. For this example and for this example only. There's a mode selection. There is a right command and a not left command. When it's in 1, it's in right mode. When it's in 0, it's in left mode. There's a clock pulse, there is a clear, and there's obviously our D input. And there are, like I said, D is always held low. And I've got 4 parallel outs right here. But I've also technically got 2 serial outputs. What is my serial output when it's in right mode? It's this one. What is my serial output when it's in left mode? It's this one. So be aware that you pick and choose. How do I do a timing diagram like this? Well, I've got to have an initial state. I've got to know what my D inputs. I got to know what my clock inputs are, and I got to know what my modes are. So just think about right 1, left 0. So right, left, right, left, right. What was I initially? I was initially 0, 1, 0, 0, red to pink. Just go ahead and put 0, 1, 0, 0 on our timing diagram. Okay, so that's what 0, 1, 0, 0 looks like on our timing diagram. And now just figure out what modes are there for each one of those clock pulses. Looks like 1 and 2 is going to be right, 3 and 4 left, 5, 6, 7 right, 8, 9, 10 left, 11 and 12 right, and just go ahead and you can write those little cheat sheet notes for you right there on the side of that tabular format. So if we were initially in 0, 1, 0, 0, we're shifting right. The 1 goes there, 0 goes there, that 0 goes there. What's being shifted in? Well, D is always being held low. So we will always shift in a 0. We're again shifting right. 1 goes there, the 0 goes there, the 0 goes there. What's being shifted in? Well, D, it's always a 0. And now we're in left mode. Okay, what happens now? Well, all of our examples that we've done thus far have been right. What do? They shift left. So this 1 goes there, that 0 goes there, this 0 goes there. What's being shifted in? Well, again, D is being held low. What I've told you is basically we have a single serial in, and it's acting for both serial left in and serial right in. It's being a 0. Okay, we are in left mode again. That 0 is shifted there, that 1 is shifted there, that 0 is shifted there, that last 0 being shifted out. What is being shifted in? Well, still D being 0. So all we're doing is we're just kind of bouncing things back and forth now. Let's go ahead and see what happens when we shift it right 3 times. We shift 0, 1, 0. What's shifted in? That D input 0. We're again shifting right 0, 0, 1. What's being shifted in? 0. Finally, we're shifting right again. What happens to that 1? It's out of there. It's gone. When we shift left, what's going to happen? It's not going to be shifted back in. That 1 is not going to be shifted back in. What's being shifted back in? D. Okay, it's 0. So now pretty much all we're doing is we're left shifting zeros and shifting in 0. Left shifting zeros, shifting in 0, right shifting 0, shifting in 0, right shifting zeros, shifting in 0. Just like our other diagrams, we can go ahead and take that vertical representation of the column, lay them down horizontally. We should get a timing diagram that looks like this. And so our timing diagram, if you're looking at it again, it's right shifting. It's right shifting again. Okay, what's happening? It's left shifting. So it was a 1 on the pink. It's shifting it back to the gray bit. Okay, so it's, I know it's hard to describe this. So let's describe going down is right, going up is left. So now we're again in right mode. Right mode. What happens again? This final one, it's shifted off because it's still in, as you guessed it, right mode. All that's doing, if it has initial conditions on it, and let's say for this example and this example only, D is being held low, all you've got to do is just figure out which mode it is, each one of those clock pulses, and you'll see that they shift and behave accordingly, passing that information back and forth. And as we see, after clock pulse 7, we've shifted all the 1s out. All we've got is 0s, and if the only thing that's coming in is 0s because it told you the D is being held low, that's the only thing we're going to shift back and forth is 0s. So let's go on to another example. Okay, so here is another very similar example of a 4-bit bidirectional shift register. The only difference between this one and the last one is that, in fact, I have defined MSB to LSB arrangement, whereby this is the MSB, that is the LSB. Okay, we are initially loaded with the number 0010, MSB to LSB. What is that number? That is 2. It is not 4, okay, because we're going from MSB to LSB, right to left. You'll see something neat which happens here. Additionally, what I'm going to do is I'm going to throw a twist in here. I've not been using this clear input. Let's say between, let's just say right here, there's an active low clear issue between clock pulse 9 and 10. And what's going to happen? Things going to get cleared out. We'll see how things behave from there. But I want to illustrate something pretty critical here. Which mode are we in for every single one of those clock pulses? 1 and 2 right, 3 and 4 and 5 left, 6, 7 and 8 right, 9 left, 10, 11, 12 right. So just go ahead and put that down in the tabular format. Okay, so what we have is following modes for each one of those clock pulses. If we initially have the number 2 there and we shift it right, which way are we shifting it? It doesn't matter for MSB to LSB. We are still shifting it right. So what happens is we were at 0, 0, 1, 0. What are we doing? We're shifting it right, and we've defined right, and well, basically we define right as right. What's going to happen? So let's go ahead and use our tabular method here. 0, 1, 0, 0. It's shifting 0, 1, 0. What's being shifted in? D is held low. We should get a 0. Okay. So look at the number. We went from 2 to 4. Mistake on that one. Let me go ahead and redo that. Okay, so this is another very similar example of a bidirectional shift register, and the only difference that I've done in this example versus the last example is I've defined MSB to LSB. It will still shift right. Right is right, this direction. Where's left? It's the opposite direction. That's left. I'm going to give you the following conditions. D is held low. D input is always held low, and it is loaded initially with the binary equivalent for the decimal number 2. And additionally, I'm going to throw a little loop in here. We have not been using these clear inputs, but let's say between clock pulse 9 and 10, I'm issuing an active low clear, i.e. the clear has been held high, and suddenly at this moment the clear goes low and it immediately comes back up to high. I'm not drawing on the timing diagram because I just want this thing to fit into a single screen. How are we going to do this? Well, my first thought is to just go ahead and figure out what mode it is for every single one of those clock pulses. So I'm going to say first 2, probably right mode. The next 3 are going to be left mode. What happens? Go ahead and fill out the tabular format for every single one of those modes. There you go. And I'm going to do some indication that between 9 and 10, there's going to be a clear. And again, what are those clear inputs? Those are asynchronous clears. The moment that that clear signal is given, it will instantly clear out. It doesn't have to wait to a clock edge. The hardest part of this whole thing is where does 2, the decimal number 2, when converted to 4-bit binary, is 0, 0, 1, 0. And if you put 0, 0, 1, 0 in here for your initial conditions, you're absolutely wrong. The reason why is because I have defined this as the MSB. Okay? Again, you can use this in whatever shape you want to, but for this particular example, the right one is the MSB. We'll see how this thing behaves as we give these respective rights and left shifts there. So what happens? When we shift it right, the 0 in Q0 is going to go to Q1. 1 in Q1 is going to go to Q2. The 0 in Q2 is going to go to a 0. What's being shifted into Q0? Well, I've told you D is constantly being held low. 0. We're in right shift mode. Again, what happens? Q0 goes to Q1. Q1 goes to Q2. Q2 goes to Q3. What's being shifted in this example only, I've told you D is being held low, 0. Okay, now stop right there. What has happened to our number? We were 2, reading it right to left, 0, 0, 1, 0. We're at 4. We're at 8. Do you see what's going on? Every time we shift it right, we multiply by 2. 2 times 2 is 4. 4 times 2 is 8. And if I had a 5-bit shift register, I could create 16, 32, so on and so forth. So every single time I shift this thing right, when I've defined my MSB as the rightmost bit, I am in fact multiplying. What would happen if I shifted it left? Well, chances are I would go 1, 0, 0, shift in a 0 because D is being held low. Then I would shift over this way, shift in a 0 because D is held low, shift the following in, and shift in a 0 because D is being held low. What have I gone to? Okay, if I'm shifting left in this particular case, I was at 8, now I'm at 4, now I'm at 2, Now I'm at 1. So what I'm doing is this lazy math. If I want to shift it, if I want to multiply it by 2, shift it right. If I want to divide it by 2, shift it left, provided I'm shifting in zeros for those particular occasions, and provided I've got my MSB defined in this direction, i.e. to the right being my MSB. So that is a super cool application for some of these shift registers, especially these bidirectional shift registers. I'm doing multiplication and division by 2 every single time I shift it right or left. Let's go ahead and figure out what's happening for the remainder of this tabular input, and be aware what happens between 9 and 10. It's cleared out. Your tabular format should look something like this. So there you go. In right mode, I'm shifting it right. In left mode, I'm shifting it left. I've cleared it out at that moment for the remainder of its zeros. Okay, so we should be able to take our columnar format, slap it down on our timing diagram. Our timing diagram should look something like this. Be aware, at that moment is when it clears out, not clock pulse 10, not clock pulse 9, because it's an asynchronous clear. It should look something like this. And there's my best estimate of the timing diagram. And if you could think again, is shifting it from Q0 to Q3, that's right. Shifting it from Q3 to Q0, that's left. What are we doing? We're shifting right, right, left, 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 right, 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 left. Issue the clear command. Everything's clear from that point beyond. And again, we could do that same analysis. It was a 2, MSB to LSB. It was shifted right. It becomes a 4, MSB to LSB. Shifted right becomes an 8. Shifted left, 4, 2, 1, multiply it, 2, multiply it, 4, multiply it, 8, divide it, 4, clear it. Okay, so another classic example, in this case of a bidirectional shift register, lazy math, multiplication, division by 2. Let's do one last example. Okay, this I've been previously just holding D low. What happens if the D has an input? So in this particular case, you're going to have changing D inputs and you're going to have changing modes, and you may have an initial condition on it. Okay, let's go ahead and see what an example problem like this looks like. Okay, so here's an example of a bidirectional shift register where I do have D input now. And additionally, I've got a mode command, which I haven't drawn. So let's go ahead and put in some mode command. Okay, so now we've got a mode and a D input, and I've got an initial state. I've given you right here. It says it's initially clear. Go ahead and see if you can fill out the tabular format. Go ahead and put those modes in there, and be aware that that D input is changing for each particular clock pulse. Let's say that I'm not issuing any clears throughout here besides that initial clear. Go ahead and figure out what the tabular format may look like. So I've filled out my initial clear, I've filled out my modes. Additionally, look what I've done to the D inputs. I've gone ahead and sampled every single positive clock edge what that D value might be. And I can put that off to the side if you need to on your tabular format. At clock edge 1, D is a 1. At clock edge 2, D is a 1. At clock edge 3, D is a 0, so on and so forth, filling out the remainder of that column. But now the point of basically staying organized, when it's in right mode, where does that input go to? When it's in left mode, where does that input go to? And additionally, notice, look at how I've defined these. I am going from MSB to LSB. Shifting it right takes the MSB down to the LSB. Shifting it left takes the LSB up to the MSB. Okay, so again, how you use these things is your choice, how you define them. Go ahead and figure out the columns for the Ds. Figure out where the D is going for those rights and lefts, and figure out the tabular format. Let's go ahead and see if you get something that looks similar to this. So our first mode, for the first clock pulse, we shift right. Q3 goes to Q2, Q2 goes to Q1, Q1 goes to Q0. The 0 that was in Q0 is out of there. What's being shifted in? That D. Where does it go to? It goes to 1. Okay, we are in right mode again for the second clock pulse. 1 goes there, 0 goes there, 0 goes there. The final 0 is kicked out. What is being brought in this particular case, the D input. We're in right mode again. 1 goes there, 1 goes there, 0 goes there. 0 in Q0 is kicked out. What is kicked in? A 0. Again, we are still in right mode. 0, 1, 1. The last 0 is kicked out. What is being shifted in? 1. And now we're shifting left mode. Fifth clock pulse, we shift left. Q0 goes to Q1, Q1 goes to Q2, Q2 goes to 0, the 1 is shifted out. What is shifted in? What's the D input? At the fifth clock pulse, it happens to be a 1, and it's assigned to Q0, 1. So now go ahead and shift over left in this particular case, shift in a 1, shift over left, shift in a 1, shift over left, shift in a 1, shift right, shift in a 0, shift right, shift in a 1. Okay, so you see what's going on. See if you can go ahead and do these last two. They should look something like this. And the remainder of our tabular format should look something like this. Go ahead and take those columnar representations of Q3, slap it down in the horizontal timing diagram, do the same thing for Q2, Q1, Q0, and your timing diagram should look something like this. And that's what our timing diagram should look like. Now, be aware the only difference between this example problem and the last example problems is the fact that we've got some input on D, whereas those previous ones were always D is equal to 0, or if it was constantly being held to 1. In this particular case, we've got a changing input on D. But if you think about what's going on here, especially here, we are in write mode in this particular example, particular section. What's happening to that 0 that's on Q3 being shifted to Q2, Q1, Q0? What happens to be shifted in during those time frames? Well, it's this particular block 0, 1, 0, 0. Before we finish the lecture on the bidirectional shift register, what I want to do is talk about a particular fixed function integrated circuit, namely the 74194. Why you would use anything other than this thing is beyond. The 74194 is truly one of my favorite fixed function integrated circuits for shift registers, and because of this phrase, universal, you can use it as a serial input or a parallel input. You can use it as a parallel output or a serial output. Additionally, you can have bidirectional, left or right. And there's actually really 4 modes, and we're going to go ahead and talk about these things individually here. There's it's a positive edge clock. Okay, so there are synchronous inputs. Anytime you're moving left or right or loading, you're going on the positive edge. Okay, there are 2 serial inputs, whereas our previous examples, I've been tying the serial left input and the serial right inputs together into a single D. Be aware the 74194, it's like I said, it's universal. It has 2 separate serial inputs. Okay, and in this diagram here, pin 2 serves as the shift right serial input. Pin 7 serves as the shift left serial input. If I wanted a single input to that, just tie pin 2 and 7 together. The parallel inputs, where are they? They're right here. Pins 3, 4, 5, and 6. Be aware that some data sheets for the 74194 show those parallel inputs as Ds. Some show them as Ps, like I've been doing those previous diagrams. And long story short here, when a Rome do as the Romans do, if they call them Ns or if they call them Xs, they're Ns and Xs, okay? But what I've been trying to do in these past diagrams is show you parallel inputs are Ps. In this particular case, they're Ds. We've got 4 parallel outputs right here, okay? And 2 serial outputs, okay? When I say you can be used as serial out when it's in shift right mode, what is my shift right output? Pin 12, Q3, because I've defined it MSB to LSB in that particular case, because Q0 is to the left, so I'm shifting it right to the Q3. Where is my serial output when I'm shifting left? Obviously Q0, pin 15. I've got 1 clear, an active low clear, and like I said, there are 4 modes. How do I define 4 modes? Well, I have 2 inputs, S1 and S0. When S1 and S0 are both being held low, it's called an inhibit. Basically, whatever's on Q3 to Q0, stay on Q3 to Q0. Don't shift them right, don't shift them left, don't do nothing, just sit there. Okay, so it just stays. However, when I want to go in right mode, I take S0, S10, S01, and it shifts right. What's right? Well, right. 0, 2, 3. Now I switch it. I take S11, S00. I'm in left mode. Which direction do I shift? I shift left. Finally, the last of the 4 modes, I take S1 high and S0 high. What mode am I in? I am in load. And notice it is a synchronous load, okay? It requires that positive clock edge to clock those D3 to D0s to the Q3 to Q0 outputs. Again, one of my absolute favorite devices. We have probably already used this thing. As a matter of fact, I know we have, and we're going to potentially use this thing in the future. You can use other shift registers, fixed function integrated circuit, but why would you want to when you've got this thing and you can do pretty much anything you want to it? Okay, this concludes bidirectional shift registers. And let's just go on to some specific applications of shift registers in configurations that can potentially enable them to act kind of like a counter.